Hi, this is a little bit of a narration through the Conics PowerPoint that you are going to find on Canvas for Conic Sections. The PowerPoint will also be on there so you can click back through the slides, but some of these I thought would be best if you had a little narration along the way. So on this opening page, you can see some conic sections that are graphed up here. You can see how a conic section is dissected, and you can see some different views of the two specific ones we're talking about today. The conic section is derived, or is basically from dissecting a cone. So hence the name conic section. We're focusing a lot on ellipses and hyperbolas today. So what you should be able to do once we're finished with today's lesson is know the four conic sections by definition. We're focusing on dissection definitions. However, there are algebra definitions. We're just not going to focus on that right now. Understand the basic shape of each conic section. You're not going to be asked this year to actually graph these things, but they do come back in our next topic, which is parametric equations, and they do come back in Calculus BC for those of you that are going to take BC. Be able to identify the type of conic section in two forms: general form, which is an equation that is the same for all four types of conic sections, and then standard form, which is a unique equation to each type. So each of those looks a little bit different. You need to be able to identify them by looking at either form. You need to understand how to change forms of a conic section, and that's where good old completing the square comes back into play. We practiced that last year. You've looked at it in Algebra 1, so hopefully we'll just do a quick review on that at the very end of this lesson, and you'll be okay. Previously, you have learned about two of the four conic sections. In Algebra 2, last year we studied parabolas. We looked at parabolas which open left or right. Conic sections are quadratic in nature, but they aren't necessarily functions. Circles you learned about in geometry, and that would be a circle with the origin at the center, circles where the origin isn't at the center, all of the characteristics of circles. You spend a lot of time in geometry on circles. Today we're looking at ellipse and hyperbola, which will wrap up the four different conic sections that we have. So the review from what you should know: the circles, that's what you did in geometry. So the circle, if it has an equation of 0, 0, then the equation is x squared plus y squared equals r squared. So that's the radius squared. If the center of the circle is not at the 0, 0, then it's going to be at this HK point, and that goes into the equation, and that's your translation in the H direction and the K direction. Be really careful here. Remember that the equation of a circle is equal to the radius squared. So if this number is, let's say, 49, then you don't tell me the radius is 49. You would tell me the radius is 7, because we're going to take the square root of r squared to actually get our radius. In Algebra 2, we learned about parabolas. We use this 4p form, where 4p is on the side of the equation that is not squared. And we looked at vertical and horizontal, vertical ones being functions, horizontal ones being not functions. The h and k is the vertex in the parabola. And notice here that this equation is h then k, where this one is k then h. That's really not super important because you can kind of go about figuring out which way a parabola is oriented by a couple of different methods. But the important thing to point out here is that the h always stays in the same parenthesis with the x, whether it comes first or whether it comes second, and the k always stays with the y. So as these shift directions, pay attention to where you put your h and your k. Our textbook, if you want to find conic sections, you can use it as a reference to look up. And in our textbook, that's in Chapter 9. And you can find information about ellipse on pages 647 to 648, and hyperbola from 656 to 657. So you can definitely use your textbook as a resource. The definitions we talked about making sure you're familiar with are the dissection definitions. So the dissection is what we're talking about here, and it refers to a double nape cone. A double nape cone is this cone down here in the hyperbola box, where you have two cones turned upside down that meet at that little point. There is an axis that runs from the top all the way through that point, all the way out the bottom, and this is considered a nape, and this is considered a nape. So it's not that you're going to have to give necessarily the definitions, but it's important to know about the definitions because that also lets you know a little bit about the conic section itself. So if we take this circle and we dissect it with a plane perpendicular to the base, then we're going to get a circle. And depending on where you dissect it, depends on how big the circle is. It intersects exactly one nape and is perpendicular to the axis. Remember, the axis runs this way, so that's perpendicular. An ellipse also going through one nape is going to cut through the plane at a diagonal, doesn't go through the base. So it intersects one nape and it's not perpendicular to the axis. A parabola is also one nape cone. It goes at an angle, but it goes through the side all the way down through the base at the bottom. So it intersects one nape and is parallel to the element. So the element is the outside, so you can see the parallelness of this with the parabola in here. And then finally the hyperbola, which is the unique one because it actually goes through both napes of the cone. So the plane starts up here through this base, through this nape, all the way out through this base. So we say that it intersects both napes and parallel to the axis. So those are the 4 definitions by dissection. Here are a couple of examples of ellipses. It's that oval shape right there. The one that's really well known is Statuary Hall at the U.S. Capitol building. And basically, it's rumored that John Quincy Adams would sit at his desk on one end of this room and he could eavesdrop on conversations at the other end of the room because of the placement of the desk. And it was an oval room with an oval ceiling, with an elliptical ceiling, and the waves would bounce off the ceiling and down to the other desk, which we call the focal point. And if you're ever on the tour and your tour guide's any good at all, this is where your tour ends, is in the Statuary Hall. And there's a little gold seal kind of somewhere on this end of the room, and there's another gold seal on this end of the room, and your tour guide will usually drop you at one seal and he'll talk to you and then he'll start backing away, and all of a sudden you can't hear him. And then when he hits the focus on the other side of the room, the focal point, all of a sudden you can hear everything he's saying even though he's on the other side of the room. So that's pretty cool. If you ever get on that tour, pay attention to where you end because that's kind of a fun fact there. If we were in class, we would be doing a paper folding activity for ellipses and hyperbolas, just like we did last year in parabolas. And we would take a circle and we would have our center marked, and then we would put another dot somewhere inside the circle. And then what we would do is take this dot and we would fold it up to the edge of the circle and crease it and unfold it. And then we would keep folding from this dot to the edge all the way around the circle. And what will happen when you fold that paper like that is you end up with this elliptical shape in the center. So I'm going to take the circle that we would have drawn away and I end up with this shape. So I have these 2 points inside here. Those are called the foci, or focal points. And then between the 2 focal points is what we call the center. That's where our HK is. And if we take a line and connect all 3 of those points together, ending on the edge of the ellipse, we get what we call the major axis. So this is kind of like an egg shape. It's definitely longer in one direction than the other. So the longer side is the major axis. And then if we draw a line perpendicular to that through the center, we get the minor axis. At the end of the major axis are the major vertices. At the end of the minor axis are the minor vertices, or sometimes we call them the covertices. The direction of the ellipse, whether it's going to be bigger going horizontally or bigger going vertically, all depends on where the major and the minor axis are. So in most things, when you see the equations in standard form, you're going to be referenced to 2 equations. Notice that each of these are fractions. They're connected with a plus sign and they equal 1. So when they equal 1 and we have them in this form, we can look at the top and get our HK values, which is the center. We can look at the bottoms, a squared and b squared, take the square roots, and we can find the length of the major and minor axes. And then from the equation itself, we don't really have to memorize both of these equations. We just have to know which way goes which direction. And so we can do that by, if you notice, the x is first here and the x is first here, but what's changing? The numerators. You have a squared and b squared down here, and you have b squared and a squared down there. Well, here's why that's important. When you're trying to determine the direction, or we call the orientation of the conic section, you look at the largest denominator, and whatever's above it tells you the direction. So in this case, if a squared is the biggest denominator, then x is above it, so it's a horizontal ellipse, meaning bigger in the horizontal direction. if b squared is bigger on the bottom and it's below the x, or the x is above the b squared, then that tells me that it's going to be longer in the vertical direction. So I don't really have to memorize two equations. I just have to remember that I'm looking for the biggest number, and that will tell me which direction it's going to go. Okay, so the second conic section is hyperbola. We have the McDonald Planetarium in St. Louis, Missouri. The whole building is it's got hyperbolas on both sides. The Fermilab has a whole bunch of hyperbolas all over the place, from the glass to the outside of the building to a lot of statues around it. So those are kind of fun. And the paper folding activity for hyperbola, we would take our circle and we would put a dot somewhere in the circle, and then we would put a dot somewhere outside the circle. So remember, the ellipse, we put the two dots inside. On the hyperbola, one's inside and one's outside. And then we take that dot and we put it over on top of the edge of the circle and we crease it, and we keep doing that and fold that dot all the way around the circle. When we do that, we get these little branches that form. They look like two parabolas. And so that's how the hyperbola develops, and we have 2 points. Remember, this was inside the circle, this one was outside. Those are called the foci. So in this case, the foci is inside of each parabola. Remember, in an ellipse, it was inside the whole ellipse. And so we have a point right here between the two foci, between the two branches. That's our center point. And when we connect where the vertex is on each of these branches through the center, that's what forms our transverse axis. And the transverse axis tells us the orientation of the hyperbola. So that's kind of an important thing to know. I always say identify that transverse axis before you decide what the graph is going to look like, and that will help you not make some careless mistakes. Now, this one has a few more pieces to it because it also has asymptotes that run through the center point and that go inside the branches, and they are used to guide the branches to help in the graphing process. So it's going to get close to the asymptote, go through the vertex, go back outside close to this part of the asymptote, and have the focus point or foci right there. Now, if you take and go perpendicular to the transverse axis, there is a second axis here. It's called the conjugate axis. Remember, we had two axes in an ellipse. We had major and minor. Well, in a hyperbola, we have transverse and conjugate. So if I go to the end of the transverse axis and the end of the transverse axis, the end of the conjugate axis, and we notice the points that are on the asymptote along the way, it forms this little box here in the middle. So you'll oftentimes see that little rectangular box used when you draw hyperbolas. Now, if we were going to spend a lot of time graphing it, we would learn how to write the equations of these lines, or we would find the slope of the line and go through the center. We would do a lot of things like that. We're not going to spend a lot of time on graphing, but there are a lot of pieces, so I just wanted you to be familiar with the pieces of the parabola. Excuse me, the hyperbola. All right, so the equations look very similar to an ellipse. However, notice since they are still both fractions, but this is always minus, and this is going to still equal 1. Anytime you're doing and changing forms, please always remember that whatever is the minus fraction always needs to be back here, because remember, subtraction is not commutative. You can't do it in any order, so it's very important that you always remember the subtraction goes to the back. Okay, so now let's look at these two equations. We have x first here, we have y first there. So that's different, right? Now it's the x and the y changing, not the bottom numbers. So a squared will always be first in both equations. B squared will always be first in both equations. We just figure out the orientation by looking at the very first numerator. So since x is first in this numerator, it means that the transverse axis is going to be horizontal. And then the branches will open away from the transverse axis around the foci. In this one, y comes first, so that means it's going to be vertical. So the transverse axis is going to be graphed vertically, and then the branches are going to go away from each other and go around the foci. Okay, you still have the 2a for the length of the transverse axis, just like 2a was the length of the major axis, and 2b is the length of the conjugate axis, and in ellipses, 2b was the length of the minor axis. So that's different. You don't really have to memorize the two equations as long as you understand how to identify what you need out of each equation. In World War I and World War II, the long-range navigational system called the Loran was developed and used. The system was based on the shape of the hyperbola. So two stations would send out a signal at the same time, and a ship would note the difference in the times at which it receives a signal. Then it would use that information to locate where the ship is on the hyperbolic curve. So for instance, it sent out a signal here, it sent out a signal here, and then that they're able to calculate where it is on the curve, which is pretty cool at the time, considering that they didn't have GPS, they didn't have to be in line of sight. They could literally use the math to figure out where all of those big ships were, so that was pretty cool. A couple of fun facts. We know that comets travel on a parabolic, elliptical, or a hyperbolic orbit. So you probably have looked at that in your science classes a little bit. The comet that comes close to another object but never returns to it is on a hyperbolic path. It's like a slingshot, if you will. The two light shadows on the wall of a cylindrical lamp shade form two branches of a hyperbola. And then a sonic boom shockwave formed along the ground by a plane traveling faster than sound is one branch of a hyperbola. So there's a couple of little things there. Okay, so the next thing we need to worry about is how do we determine the different forms? We just talked about the different standard forms, being two fractions, one's a plus equal to 0, two fractions, one's a minus equal to 0. But in general form, that's a lot harder to see because all of them can have this big, long, ugly equation. So ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. So all of these are true or have pieces in the general form of the equation. So then it becomes our kind of chore, how do we tell which is which? Because all four in this form are going to look exactly the same. And so the reason we would want to know that is if we need to change forms, if we need them in a standard form to be able to get information out of them, then I have to change forms. And if I don't know what it's supposed to look like in the end, that can be problematic. For instance, does it need to have fractions when it's done? Does it need to be set equal to r squared? I mean, all of those things that we've talked about. So it's real important to be able to identify that. So on the next slide, there is a flow chart that asks you 4 questions to help you figure that out. After you do it a couple of times, you're not going to think about this flow chart ever again, but it's a good way in the beginning to kind of get you having that inner dialogue and analyzing what's going on so that you can figure out for sure what kind of conic section it is, and then you'll know how to turn it into the standard equation that you might need. So the first thing you're going to ask yourself, you're going to be looking at one of those big long equations with all that stuff in it, and you're going to say, is either x squared or y squared missing? And if you say yes, then you're going to know right away that that's the parabola, because of the 4 conic sections, the parabola is the only one that has either x squared or y squared, but not both. If you say no to that question, then the next thing you want to ask yourself is either x squared or y squared negative? Okay, if just one of them's negative and you say yes to that question, then you know you have a hyperbola because it's the one that has one positive fraction and one negative fraction. If you said no to that question, then the next thing you would want to ask yourself is, do x squared and y squared have the same coefficient? If you say yes and they have the same coefficient, which could be -2, -2, or could be +4, +4, then you know it's a circle, because a circle is going to have the same coefficients, so that, if you will, the major and the minor axis would be the same length and make a circle, not an ellipse. And of course, if you say no, then there's really only one thing it has left, and that is x squared and y squared have different coefficients. So they would have the same sign, but different coefficients. And in that case, then we know it's an ellipse. So this just helps you kind of sort through how to narrow down quickly and not spend time wondering which kind of equation it is in general form. So this slide just has some that you can practice. So if I look at one, x squared and y squared, that would be your a and your b from the general equation, are the same sign with the same coefficient, so that has to be a circle. On 2, we have the same sign but different coefficients, so that has to be an ellipse. On 3, only one thing is squared, so that has to be a parabola. On 4, both terms x squared and y squared are the same sign, but they have a different coefficient, which makes that an ellipse. On 5, they have different signs, so that has to be a hyperbola. On 6, they have only one thing squared, just the x's are squared, so we know that has to be a parabola. On 7, we have the same sign and the same numbers, so we know it has to be a circle. And finally, on 8, we have different signs, so we know right away that has to be a hyperbola. So that's kind of the process of going through to determine in general form what it's like. Hopefully, after our slides earlier, you can kind of go through this pretty quickly and determine in standard form which type of conic section it is. So on number 9, it's 2 fractions plus sign equals 1 has to be an ellipse. On 10, 2 fractions minus sign equals 1 has to be a hyperbola. On 11, only one thing is squared, so this is in the 4p format, which means it has to be a parabola. On 12, x squared and y squared equal to 25 has to be a circle. And finally, 13, 2 fractions minus in between equal to 1 has to be a hyperbola. So it's pretty easy in that form to know what those are going to look like. So you need to be able to identify from either form. Now, this is the last thing that we're going to talk about. You don't have to spend a ton of time working on these problems, but you should be able to know a little bit about them, because if I know what this is in general form and I know then how to leave it in standard form, I can use the process of completing the square to take care of that. So I'm going to go through one question here, just real quick review from what we did in Algebra 2 when we learned how to complete the square, or when we revisited it, because actually the first time you saw it was in Algebra 1. The Canvas page for today has another document that has 2 more worked out with some thought bubbles and some notes. If you need to see 2 more worked out, that paper is there for you. Okay, so the first thing we have to do is look at that general form and figure out what kind of conic section it is, so I know exactly what it's going to look like. So I use my strategy from the flow chart, and I go, okay, well, x squared is positive 4, y squared is positive 9, so they're the same sign, different numbers, so I know it's got to be an ellipse. Then I'm going to move the constant number to the other side. Once I do that, I have to remember from Algebra 2 that when we complete the square, whatever's in front of the square term has to be 1. It can't be any other number, so we have to factor that out. And so I pull the 4 out, and then I'm going to add something to it, and I pull the 9 out, and I'm going to add something to it. Then I would recommend at this point coming to the other side and putting plus 4, because remember we pulled the 4 out here, so to keep that balance, whatever I add here has to also be multiplied by 4, and that's what that is. And so since I pulled a 9 out here, whatever is inside is also going to be multiplied by the 9, so it also happens on this side. I find students that go ahead and take a minute and do that from the beginning are less likely to forget to multiply by 4 and 9 on that side. Not a have to, just a suggestion. So then we're actually going to complete the square. So to complete the square, we take half the middle term, so half of negative 4, we divide it by 2, and then we square it. And then we take half of this one that we're completing the square for and square it. And then we add those numbers to both sides. So that's what that's going to look like. I don't care if you leave it factored like this or you go ahead and put the number on this side as well. That's totally up to you and your method. Some people leave it this way so it's less confusing when you factor, but that's totally up to you. So then once we've completed the square, this is a perfect square trinomial that's going to factor down to 2 of the same binomial, and this is a perfect square trinomial, so that's also going to simplify down to 2 binomials. So I cleaned up this side. 4 times 4 is 16, 9 times 1 is 9, and then I worked on the factoring on this side. So remember, negative 4 divided by 2 is negative 2, and when I factor that, I get that. So now, in last year in parabolas, we would look at the 4 and the 9, and we would say, okay, what can we divide by that's going to get rid of 4 and 9? But remember, we want 2 fractions and we want it equal to 1. So this time when I complete the square, I want to figure out how to get rid of 36, and I do that by dividing everything through by 36. So that's why it's kind of important to know where you're going so you know what you need to do at this point. So I divide everything through by 36, simplify my fractions, 4 over 36 and 9 over 36, and that brings me to a standard equation of x minus 2 squared over 9 plus y plus 1 squared over 4, which equals 1. So that's the standard equation. So that's the process of completing the square. Remember to factor this out to begin with. That's important. Remember that you have to multiply to both sides. So remember, last year in parabolas we only had to worry about one thing squared if we were doing parabolas, and so we only completed the square for that one item that was squared, but when we did circles we completed the square for both. Okay, so this last slide, it's just if you want more practice or you feel like you need more practice, the equations are there, and then finding some information is there too, but definitely nothing you have to worry too much about. Just make sure that you're good to go with the different forms. So on Canvas, on the page on Canvas for today's lesson, I included the extra page with 2 more completing the square problems worked out. There is also a file called Conic War, which we were going to do in class, but so I went ahead and attached it. But basically, it is a really quick activity to help you practice looking at an equation and identifying right off the bat which kind it is. So what it is a grid, and each box in the grid has a conic section in it of the different forms, general form and standard form. And so what we were going to do in class is we would set the timer for 3 minutes, and then you would flip the conic war over, look at the question and go, oh, that's a hyperbola, put down an H. That's a parabola, put down a P. That's a circle, put down a C. And you would go through all 24 questions in 3 minutes, identifying which type of conic section it is. So if you feel you want that practice, I went ahead and put the PDF of that activity on Canvas. However, don't look at the last page until you've answered all 24 questions. The answers are on the last page of that document. I wanted you to have them in case you wanted to use that as a practice tool. But that's kind of fun and quick and an easy way to make sure you have it. In addition, I think there is this PowerPoint that's not narrated, so you can just kind of flip through and you don't have to listen to my voice. So hopefully this helps a little bit. This is something we would have done in class. It is not a full unit. It's not really going to be assessed too much, but it does come back up to play in parametric, so it's kind of important that you know those different forms now. So that's it for me. Thanks, and I will talk to you next time. Next time we're going to start parametric equations.